Welcome to Ola101. With Ola, shape your unique Web3 journey in your own way. Ola101 Episode 2. In the previous video, we introduced what ZK is and how it can be used in ZK-rollup to solve blockchain scalability problems. In this video, we will uncover the inner workings of these proofs and understand how they maintain the integrity and security of transactions in a ZK-rollup system. Let's get started. Before transactions are accepted, the ZK-rollup operator conducts a series of customary checks. These checks involve verifying various aspects such as the existence of sender and receiver accounts within the state tree, ensuring sufficient funds in the sender's account, validating transaction correctness, and verifying the match between the transaction and the sender's public key on the rollup. Once a sufficient number of transactions have been collected, the ZK-rollup node aggregates them into a batch and prepares inputs for the proving circuit. These inputs are then compiled into a succinct ZK proof. Let's explore the components of this proof. The proof includes a Merkle tree that encompasses all the transactions in the batch. Additionally, it consists of Merkle proofs for each transaction, demonstrating their inclusion in the batch. Furthermore, there are Merkle proofs for each sender-receiver pair within the transactions, providing evidence that these accounts are indeed part of the rollup state tree. Lastly, the proof incorporates a set of intermediate state roots derived from updating the state root after applying state updates for each transaction. These updates involve decreasing the sender's account balance and increasing the receiver's account balance. The proving circuit executes the validity proof by iterating over each transaction in the batch. It mimics the checks performed by the operator before processing the transactions. Let's delve into the process. The proving circuit begins by verifying the existence of the sender's account within the existing state root using the provided Merkle proof. It then proceeds to reduce the sender's balance, increase their nonce, hash the updated account data, and combine it with the Merkle proof to generate a new Merkle root. Similarly, the proving circuit performs the same set of operations on the receiver's account. It validates the receiver's account existence under the intermediate state root, increases their balance, rehashes the account data, and combines it with the Merkle proof to generate another new state root. This process repeats for each transaction in the batch, resulting in new state roots that reflect the changes made to the sender and receiver accounts. Each update to the state root represents a specific part of the ZK-rollup state tree that has changed. The ZK proving circuit continues iterating over the entire transaction batch, verifying the sequence of updates that culminate in a final state root after the execution of the last transaction. The last computed Merkle root becomes the newest canonical state root of the ZK-rollup. Once the proving circuit has completed the verification of state updates, the Layer 2 operator submits the computed validity proof to the verifier contract on Layer 1. The verification circuit within the contract then verifies the validity of the proof and examines the public inputs associated with it. These public inputs consist of the pre-state root, representing the ZK-rollup's old state root before the execution of the batch transactions, which reflects the last known valid state on the Layer 2 chain. The post-state root, on the other hand, represents the ZK-rollup's new state root after the execution of the batch transactions, reflecting the Layer 2 chain's newest state. The proof also includes the batch root, derived by Merkleizing the transactions in the batch and hashing the root of the resulting tree. Finally, the transaction inputs contain data associated with the transactions executed as part of the submitted batch. If the proof satisfies the verification circuit, indicating its validity, it confirms the existence of a sequence of valid transactions that transition the rollup from the previous state to a new state. If the pre-state root matches the root stored in the rollup contract, and the proof is valid, the rollup contract updates its state tree with the post-state root from the proof, thereby reflecting the changed state of the rollup. And there you have it. Validity proofs play a crucial role in maintaining the integrity and security of transactions within ZK-rollups. They ensure that only valid transactions are processed and recorded, providing a reliable and efficient solution for scaling Ethereum. Thank you for watching. To learn more about ZK technology, be sure to check out our website and stay tuned for more updates on this exciting field.